Hello everyone, and welcome to today's webinar. I'm your host, Jeff Rawlings, the Bruker Nanoindentation Sales Specialist for North America. And with me today is Ryan Stromberg, Technical Sales and Marketing Manager for Microscopy Products here at the Nanoindentation Business Unit of Bruker. In today's webinar, Ryan will present topics that cover nanomechanical properties obtained via AFM-based indentation, the benefits of rigid probe indentation compared to cantilever-based measurements, as well as optional techniques such as Nanoscratch, nanoDMA, and their applications. Our hope is that in this short 30 to 40 minute webinar, we will provide answers to your questions about nanomechanical testing using the Hysitron TriboScope and your existing or future Bruker AFM. And at the end, we'll have a 5-minute question and answer session. Any questions that we can't get to during today's webinar will be answered offline by email. Okay, without any further delay, let me turn things over to Ryan Stromberg.
Thank you, Jeff. It's my pleasure today to be presenting on nanoindentation, scratch, and nanoDMA, innovations for atomic force microscopes. So essentially today I'm going to be talking about the Hysitron TriboScope instrument that interfaces with a commercial AFM and adds quantitative nanoindentation capability. This is the outline of the talk. I'll start by talking about the Hysitron TriboScope and the core technology and various components of the system. Then I'll talk about mechanical testing, the types of mechanical testing you can do with an Indenter Stylus versus what you can do with an AFM cantilever-based measurement. Then I'll talk about true load control and displacement control, which are the two modes that we use for the TriboScope instrument. I'll talk about the interface, how the TriboScope fits onto the Bruker AFM platform, and I'll finish by going through some application examples and a couple of typical material systems that you can test. So I'll start by talking about the transducer that we use, which is the core technology for the system. The transducer is a 3-plate capacitive transducer. You have 3 electrodes. You have the top and bottom plate, which are fixed, and you have a center plate, which is mounted to springs and can move up and down. The Indenter tip is attached to the center plate, and the way that we apply force is we apply voltage to the bottom plate, which creates an electrostatic attraction and drives the center plate down. So by controlling the amount of voltage that we apply, we control how much downward force we're generating. Then when the plate spacing changes, there's a capacitance change. That's calibrated to a displacement and allows us to do some load control and displacement control measurements for indentation. You can see the transducer specs on the right side. It has less than 0.2 nanometer displacement noise floor, less than 100 nanonewton for force noise floor, and about less than half an angstrom per second for thermal drift. So it's a very stable system, has low current, low thermal drift. The controller that we use is a digital TriboScope controller, and the specs for the controller are shown on the left. You have a 78 kilohertz feedback loop rate, so that is the rate at which we are monitoring the force and displacement. Very fast control system for making sure you have the force that you're applying the force that you want. You can do up to 15 kilohertz data acquisition rate, which if you want to capture something that's happening very quickly, like a fracture or some transient event, you can do higher data acquisition rates. But the system is basically this transducer that you see working in conjunction with the digital controller. Next, I'll talk about the Indenter Stylus and how that type of measurement compares to what you can do with an AFM cantilever. So for the Indenter Stylus, we have force and displacement signals which are measured independently. They're traceable to SI standards. And for example, the way that we calibrate the transducer in our office is we use an interferometer to calibrate displacement, and we use calibrated masses hanging from the force sensor to calibrate force, and traceable to SI standards. So the Indenter tip is rigid, there's no bending. We're applying a force that is normal to the surface. This is a dedicated mechanical test instrument. You can do true load or displacement control, which I'll talk more about later. You can do plastic deformation of the hardest materials. We have our own software for doing the setting up the test and doing the analysis. And in SPM mode, we're operating in contact mode, in contrast to an AFM, which has many different types of imaging modes. This is only contact mode and doesn't have all of the options as far as getting topographical images, but the imaging here is mainly used just to identify the locations that you want to test for your indents. The AFM, on the other hand, has a cantilever, which is very sensitive to small forces. So it can sense any small amount of bending of the cantilever. So it has the highest force sensitivity. Very good for applying very small forces or indenting very localized regions with a small stress field. But the spring accuracy, or the spring constant of the cantilever, you do have to make some estimates in order to calculate force. And there can also be, on harder materials, you can get some torsion or some bending, which can cause the force to be applied not entirely normal to the surface for hard materials. Of course, you do have a lot more options as far as SPM imaging. The imaging will be far superior to what you can get with the TriboScope. So for topographical imaging, you have contact, dynamic modes, you have tapping modes, there's electrical, magnetic techniques, and the AFM tips are much sharper than what we have with the TriboScope system. So far superior for topographical imaging and very good for very small forces or soft materials or small volumes of materials. So next I'll talk about the AFM frequency and modulus ranges and how this compares for the nanoindentation system, the TriboScope, versus the other capabilities of the AFM like PeakForce tapping, tapping mode, contact resonance. So with nanoindentation, we're generally focused on lower frequencies ranging from less than a hertz up to 300 hertz, and modulus ranges from megapascal up to high gigapascal range. So generally higher modulus materials. With the AFM, you can cover a wider range of frequencies up to kilohertz range, and you can also do lower modulus materials due to the sensitivity of the cantilever for these low forces. But some limitations in terms of the very hard materials, as we discussed earlier. On the right side here, you can see another plot of tip radius versus the forces or the volumes of material that we're testing. You can see that the cantilever has a typical radius of 10 nanometers or less, so it's much sharper than our typical diamond indenter that we use for indentation. So it's very sharp, it's very good for imaging and for testing small volumes of materials. On the TriboScope system, we're using a diamond indenter that usually has a tip radius of 50 nanometers or more. So we're testing at higher forces. This is micronewtons or millinewtons of force, and higher volumes of material compared to the AFM. So testing in a little bit different regimes here as far as the AFM, base measurement, and the TriboScope. This next slide shows the modes that we use. So we have load control and displacement control. The standard mode that most people use for indentation is load control, where you're increasing the force, you're starting from zero, and linearly ramping up the force. You have these pop-in events that occur on this sample, which is aluminum single crystal 100. So we're loading up, you have a couple pop-in events occurring, and the force continues to rise. And as we go deeper, we're just measuring the depth of the indenter as we go. And the other mode is displacement control. We're actually controlling the position of the tip. So we're pushing into the material at some constant velocity. And as we push in, we're measuring the amount of force felt by the tip. So on the aluminum sample here, you can see the force building up, and then you have a dislocation occurring. So the force will drop and then builds up again, and you have another dislocation. So you can actually see a lot of detail in the individual dislocation events here in displacement control. But as I mentioned, you have your choice of modes. Most people will use load control for indentation. But if you're doing a compression experiment, let's say, on a pillar material where you have a cylindrical pillar and you're compressing at some, you want to compress at some constant strain rate, then you would use displacement control based measurement. So the calibration for the system, it starts with the calibration of the transducer, which is done at our office. We calibrate how voltage converts to force or displacement. For displacement, this is calibrated using an interferometer. And for force, we're calibrating force using calibrated masses hanging from the force sensor. So this is SI traceable. These are calibration constants that we provide for your sensor. And you also need to do a calibration for the tip. So for nanoindentation at this scale, every tip has a slightly different shape. So it may be Berkovich or cube corner or conospherical geometry, but each tip has its own unique shape, and we need to calibrate that. So we do that by indenting reference material, which is usually fused quartz. So it's a smooth surface. It has a known modulus. We can do indents at different depths, so applying different forces, measuring different depths, and because the modulus is known, you can calculate what the contact area would be for that indent. So we're doing many different indents at different depths, tracking the area versus depth, and you can use this to create a polynomial function which describes the three-dimensional shape of your tip. On the left side here, you can see how the software is set up. So we have a load function editor, which allows you to do up to 2,000 segments for your test. This graph on the left shows force versus time. And so the test that we're showing here has many cycles of loading and unloading. So we're loading up, holding, unloading, loading a little higher, holding, unloading. We call this a partial unload. So you're doing many cycles and going deeper and deeper. And from each of the unloading segments, you can make a measurement and calculate area, stiffness, and even hardness, modulus. So this is one way of doing a depth profile and getting measurements at different depths on your sample. So you have your choice of load control, displacement control. You can also do constant strain rate, creep testing, stress relaxation. For the data analysis, we start with the raw data, which is a load versus displacement curve. This is essentially the mechanical fingerprint of your material. We start with a loading curve where the force is increasing slowly, and then you have plastic and elastic deformation occurring. Then we hold the force at the peak for a few seconds, and then you have an unloading segment where you're just looking at the elastic response of the material. And so based on the shape of this curve, you can do some analysis using a Oliver Farr model, which is well accepted by the community at this point. The way it works is you calculate contact stiffness, which is the slope of this line that's tangent to the top of the unloading. That's defined as the contact stiffness. You measure that. You also measure your contact area using the area function calibration that I talked about earlier. So you convert your depth into a contact area. And once you know these things, you can calculate elastic modulus of your material. You can calculate the hardness. Hardness is just the peak force divided by the contact area. And so all of this analysis is built into the software and gives you the output of your modulus or hardness for your material. Next, I'll talk about In-Situ SPM Imaging. I'll talk about how the AFM imaging works and compare that to how it works with the TriboScope. With an AFM, you have a cantilever, sensitive cantilever that bends, and then you have a laser that bounces off the top and hits a detector. And that is in feedback with a piezo scanner in the green. So this is scanning back and forth. The piezo is extending or retracting to maintain the same deflection of the cantilever. And the cantilever tips, or the AFM cantilever tips, are very sharp. They're very sensitive to small changes in topography. And so you can get very high resolution topographical images And as I mentioned, the tip is very sharp. It can ride across even the smallest features for imaging purposes. With the TriboScope, we have our capacitive transducer attached to the piezo scanner, and so now the piezo scanner is in feedback with the transducer. It operates similar to contact mode AFM, where the tip is just riding across the sample, always in contact with the sample and in feedback with the piezo. So you're able to scan back and forth. Once you find the location that you want to test, you stop the scanner, you freeze it in place, then you do your indent, and then you unfreeze the scanner, resume scanning, and you can get an image of the material and the region that you've tested and the surrounding area of the sample. The Hysitron TriboScope goes on to the various different Bruker AFM platforms. I'll show an example of how to mount this on the system. It is an easy, non-permanent change to the AFM platform. So it works with the small sample or the multi-mode AFMs as well as the large sample dimension or dimension icon AFMs. The components are a little bit different depending on the system, but we do have interfaces for the different types of AFMs. So you start by removing the laser cantilever assembly of the AFM. Slides out of this dovetail slot that you see. You disconnect the cables, and then in its place you put the Hysitron TriboScope scanner and transducer, and then you make the electrical connection. You see the piezo in the silver color and then the transducer in the black at the bottom, and this replaces the laser cantilever assembly. And so it really is as simple as that as far as switching this out. I wanted to show an early example of some results that we got from the TriboScope back in the early days. This is a gold sample with atomic terraces. So you have essentially monolayers of gold that are stacked on top of each other. And we were able to place indents on a single atomic terrace and also on an atomic step bunch. And these regions are identified through the SPM imaging mode that I talked about earlier. So you can identify different areas to test. When you place an indent on the atomic terrace on the single layer, you see quite a bit different behavior as you do when you place an indent on the atomic step bunch. So on the step bunch, the sample is relatively, there's some compliance there. It requires less force to go to the same depth, whereas on the atomic terrace, you need much more force to get to the same depth. So it's supported by the substrate underneath, and you see quite a bit different behavior depending on the part of the sample that you're indenting. So you always want to be able to image the surface and place your indents carefully, because this can have a large impact on the properties that you're measuring. This image here shows all the different modes of testing that we can do with the TriboScope. We talked about indentation and measuring hardness and modulus. We can also do a wear test, where you're actually imaging the surface, but instead of applying a low force just to follow the topography, you're actually applying a much higher force to push down and wear away material as you go. So you can do this to characterize wear volumes or scratch-resistant materials. We can also do a scratch test, which I'll show examples of, but this is where we're drawing the tip across the sample, applying some normal force, and controlling the lateral position. And overall, you can do an SPM image. So you can, once you've done your test, you can do a larger scan and just measure topography and see how you've deformed the material and the location of your test. Okay, so moving on, we will talk about a few application examples. I'll start by talking about this solder bump application. So you can see in the red here, this is a cross-section of a solder bump. Then I'll talk about thin film testing. This is a diamond-like carbon film deposited on a steel substrate. The yellow part is the DLC film, and the blue is the steel substrate. Then I'll talk about our scratch technique, wear technique, and I'll finish by talking about our dynamic capability, which we call nanoDMA. So for the solder bump material, this is an example of a printed circuit board where you have, on top of that, you have a processor, and on top of the processor, you have some memory. And these are all connected using a so-called flip chip interface. So you have solder bumps, which are primarily copper. They have a rounded solder cap on top, which is rounded after annealing. And then on the bottom here, you can see a cross-section where you have copper underneath, and then you have a softer solder material on the top. And the way that it works is you melt the solder, then you do the connection and make the bond to the memory. The cross-section topography you can see here. The copper component is on the bottom, and on the top you have the softer solder material, and in between you actually have a couple of different intermetallic phases which reduce the diffusion processes for electromigration. So this is just a cross-section and topographical image, and this is used to identify the regions that we want to test. So what we're going to do is do some displacement-controlled indents to a depth of 80 nanometers. So we're going to start from the surface. We're going to ramp up to 80 nanometer depth, then hold that depth, and then unload. And we're going to repeat this on the different areas or different regions of the sample, on the hard phases as well as the softer solder phases. So here you can see the actual indents that we've performed. In the topographical image, you can see the residual impressions of the indents in the different regions. And in the force, the load and displacement curves, you can see the different regions. So the IP is the intermetallic phase. It is much harder than the other areas that we tested, so it requires much more force, about over 1 millinewton of force to get to 80 nanometers of depth. The copper material is somewhere in between, and the solder is by far the softest, where you only need about 200 micronewtons of force to go to an 80 nanometer depth. And you can also see some interesting deformation behavior and some dislocations occurring, similar to what we saw on the aluminum sample earlier, the single crystal aluminum. So as far as the mechanical properties, you can actually calculate hardness and modulus for each of these regions. I neglected to mention earlier that we have a silicon wafer underneath, so the copper is deposited on silicon, so we also did some indents on the silicon, and also within the intermetallic phases. So that IP1 phase is very thin, it's less than a micron thick, but we're still able to target it and place some indents. So as far as the hardness, you can see that the silicon has the highest hardness. You have different hardness values for the copper and for the intermetallic phases, and much softer, much lower hardness for the solder material. As far as the reduced modulus, again, silicon has the highest modulus, and then you have decreasing modulus as you go to the copper, the intermetallic phases, and finally the solder. And so you have very repeatable measurements. There's some influence from topography, so a flatter surface will generally give a more repeatable measurement, so you want to polish this as smooth as you can. But you can also do stress relaxation measurements from a test like this. So these, if we analyze the hold segment of these indents where we're holding the force, you can actually look at how the stress relaxation occurs, and the amount of force required to keep you at that 80 nanometer depth will decrease over time. So you can see this for the different regions, for the intermetallic phase, for the copper, and the solder. The amount of stress relaxation that occurs will generally follow a exponential decay function. On the solder, the force drops from about 200 nanometers down to maybe 150 nanometers, so we're losing about a quarter of the force to stress relaxation. So you can fit this to different models. You can extract time constants for the stress relaxation behavior. You can also do the opposite, which is hold the force and measure creep properties. The next example here is for thin film nanoindentation, where you have a diamond-like carbon film in the yellow, this DLC film on a high-strength steel substrate, which is shown in the blue. We start by doing a topographical image where you're imaging the surface, and you can actually measure the step height of the film. So this is essentially the film thickness. In this case, it's 129 nanometers from the top of the film to the substrate. And of course, with the topographical image, you can also measure surface roughness of the different regions. Looks like we have nice smooth regions for testing here. So after we get an initial image, we go in and do some indents. You can do quasi-static indentation at different forces, measuring modulus and hardness. The modulus of the steel is around 200 gigapascals, and the DLC in this case is around 180 gigapascals. If we look at the hardness, you see the opposite trend, where the DLC is actually much harder than the silicon or the steel substrate. And you can see the load displacement curves on the right here, and the exact placement of the indents on the topographical image that we capture after the test. Next, I'll talk about scratch testing with the TriboScope. So in order to do scratch testing, we use a two-dimensional version of our transducer, where you have the standard transducer in the middle. This is used for controlling the motion in the indentation axis. And then on either side of that, you have two other transducers, which are used to pull the tip laterally, left or right, and control the lateral position. So it's quantitative, it's SI traceable, it's calibrated in the same way, and allows you to do scratch testing. This image of the software here shows a fairly complex scratch test where we're doing many cycles of scratching. So this is a reciprocating scratch test where we're measuring changes in friction as we continue to scratch along the same path. And in between the reciprocating scratch segments, you're just measuring the profile of the surface of the sample. So for to measure scratch resistance of a scratch-resistant coating, you can do a ramp force scratch test. So we're drawing the tip across the sample, we're linearly increasing the normal force, and on this sample you can see there's a point where we break through this upper layer, and the scratch gets much wider at that point. So with the initial profiles, we can measure this initial topography of the sample. Then we can measure the topography under load. So as we're applying the force up to 2 millinewtons of force, you can see the depth that we're going to. And then you have the post profile, which is the final residual imprint that you've left in the surface after it's recovered. But what you can do is you can monitor scratch, or you can monitor friction to identify this failure point. So as the tip breaks through the scratch-resistant coating, you'll have a change in lateral force and essentially a change in friction, which is the ratio of lateral force to normal force. So by monitoring the friction here, you can actually identify this failure point where you've broken through the scratch-resistant coating. This example is a reciprocating scratch test where we're scratching back and forth across a smooth surface and periodically measuring surface profiles. The red segments are the surface profile measurements where you're applying a very low force and just following the topography of the sample. In between that, we have many cycles of scratch where we're applying a higher force, 250 micronewtons of force, for many cycles, and then we go back to just measure the profile. So you see the original virgin profile of the surface here, and then you see the profile after we've done these reciprocating scratch tests. So it's a fairly smooth sample. You have only about 2 nanometers of height variation across a 4 micron scratch length. And you can see after that initial set of passes, there's not a lot of additional deformation that occurs, but you are continuing to sort of smooth out the surface. And you can see that in the friction measurement. So if we look at friction versus segment, you can see the friction is changing very quickly during the first set of passes as we're wearing away material, and then it slowly stabilizes, but it does slowly continue to decrease as you're continuing to smooth out the surface. So I'll finish by talking about the nanoDMA 3 mode, which is our option for dynamic testing. The way that it works is we apply a oscillating force on top of the normal standard indentation force. You have quasi-static or DC force, and then we're superimposing an AC signal on top of that, where we're controlling the load amplitude. And what we measure is the displacement amplitude and the phase. So for a viscoelastic material, if you have a soft material, a polymer or biological material that has some viscoelastic properties, we can actually measure storage modulus, loss modulus. You can measure frequency dependence of these properties. The classic example here is a rubber ball that's bouncing. It bounces, and you lose some energy, so it bounces to a lower height. And you can think of this as the storage modulus is the amount that's recovered, whereas the loss modulus is the amount of energy that's lost during the bounce. So it's not quite analogous. There's many frequencies occurring when the ball bounces, whereas in our test we're focusing in on a single frequency, but essentially it's a rough analogy for the test that we're performing. You can also do depth profiles. So as you indent, again, we're superimposing this oscillating force. You can continuously measure properties as a function of depth, frequency, and time. You can do hardness, modulus, anywhere from 0.1 hertz up to 300 hertz. You can do a single frequency and measure depth profile, or do a frequency sweep and measure properties at all different frequencies. If we go back to the DLC example, you can see we actually tested 3 different DLC films. One had 25 nanometer thickness, one had 75 nanometer, and one had 135 nanometer thickness. So we do depth profiles, measuring properties anywhere from about 10 nanometers to 150 nanometers. At the low depths, you can see a clear difference in properties between the DLC and the steel, and as you go deeper, you can see them start to converge. So what's happening here is you're actually starting to get more and more contribution from the substrate as you go deeper, and the properties of the film will begin to approach the substrate properties because of this substrate effect. But if you want just the properties of the film, you can do a very shallow measurement, and here you see clear differentiation between the properties of the diamond-like carbon and the steel. In terms of modulus, on this set of samples, we don't see a lot of difference or depth dependence as we go. If we compare our technique to the macro scale dynamic mechanical analysis, you see good correlation if you're looking at bulk materials. So this is comparing nano to macro measurements for silicone material. And you see good correlation in the case of a uniform bulk material. But of course, the macro scale measurement can only be used on bulk materials. You don't have the sensitivity to go in and make localized measurement if you have a nanostructured material or individual components that you want to test. Another capability for the nanoDMA mode is to do long-term creep testing. So this is back to our solder bump sample. We start with an image of the surface. We can actually identify the top of this rounded surface using the imaging. So we find the very top. We place an indent on the top, and we make this creep measurement. So this reference creep technique starts by having this red segment where you are ramping up the force and doing this oscillation. We use this red segment to measure the modulus of the material. And once you have measured or calculated the modulus, then we go into the blue segment where we're holding the forces. We're continuing to oscillate. The modulus is now known, and so you can actually use this equation here to calculate contact area. So we're measuring stiffness due to the dynamic oscillation, and from that we're calculating contact area, which is converted to depth. So we're applying a constant DC force over a long period of time and measuring the depth. And the advantage of this technique is that any error from drift becomes negligible. So allows you to, rather than being limited to a short amount of time where you're trying to get around thermal drift or minimize thermal drift, this technique is independent of the drift, so you can do for much longer periods of time. So here we have stiffness versus time. This is the raw data. Again, this is converted and corrected into depth versus time, and we can do this at different temperatures as well. So here we have measurements everywhere from room temperature up to 175 degrees. You see pretty consistent behavior up to 150 degrees. but as you go to 175, you can see much higher creep rates. So you're enabling some creep mechanism. The deformation behavior of the solder is beginning to change, and you're enabling much higher creep rates within the solder. So you can do this as a function of temperature as well. And you can also fit this to different models. It's an exponential decay function and determine time constants. In summary, we talked about cantilever-based measurements. We talked about the high sensitivity of the cantilever to measuring small volumes or very small forces. We talked about some of the very high-resolution topographical imaging modes of the AFM, which is the true strength of the AFM. There's tip calibration and deformation models. There's limitation in terms of hard samples, where you may have some torsional motion or some rotation of the indenter tip. So for harder materials, the indenter stylus would be preferred. For the indenter stylus, we talked about indentation and dynamic modes, hardness, modulus measurement, how those values are calculated, also creep, stress relaxation, and as well as scratch and wear testing. For imaging, again, this is only contact mode. It's a lower resolution imaging than you can get with the AFM, but it is sufficient for identifying these regions that you want to image and place your indents for quantitative indentation testing. So that's essentially the end of my talk. I'll finish by mentioning that we have some other webinars upcoming. We have an XPM, Extreme Property Mapping webinar, coming up on September 28th. This is showing some very high-speed indentation that we can do. And on October 19th, we'll have another webinar going into more detail about dynamic nanoindentation modes. So thank you all for your time, and it's been a pleasure presenting today.
All right, thank you, everyone. Please remember to join us on September 28th for the next webinar, where Dr. Eric Hinsela will talk about XPM, our high-speed indentation mapping technique. Thank you again for joining us. We hope to see you next time.